So the project is mentioned finding an upper limit on the angular momentum of a neutron star. A neutron star is the remnant of massive stars and supernova explosion. Like any star, it's in a state of hydrostatic equilibrium, which basically means that the inward pressure of its own gravity is counteracted by some sort of outward pressure. In the case of the sun, the outward pressure is thermal energy. In the case of a neutron star, the outward energy pressure is quantum mechanical degeneracy pressure, which is basically the neutrons are so close and compactified that they're almost touching, so they repel each other for the Pauli exclusion principle. Consequently, it's incredibly dense. It's denser than an atomic nucleus. For comparison, it's about 10 trillion times denser than lead. And in this matter range, this matter is so dense that it's not really well understood. So the goal is to basically study this to get a better idea of this matter. As far as physics are concerned, because it's in hydrostatic equilibrium, we have the gravitational pressure, which is, because it's so dense, is controlled by general relativity. And then we have the outward pressure, which we basically surmise by a single macroscopic equation of state, which in this case will relate pressure and density. The density, as I mentioned, exceeds the nuclear density, and so we have no experimental data on this because we can't recreate it in a lab. So in order to understand matter in this phase, we need to basically observe a neutron star and make observations of it there. And as we measure properties of the neutron star, we put constraints on and hone in on what the correct equation of state of matter is at this pressure and density range. So what we're going to be doing is trying to set upper limits on the angular momentum, which will come into play to verify the equation of state. Because, as I mentioned, hydrostatic equilibrium, we have Einstein's equation on one side for gravity and the equation of state for the pressure, quantum mechanical pressure, on the other side. So basically, the star is the solution to these two equations. And so because it's a solution, if we have a given equation of state, we can numerically integrate Einstein's equation to get results for the mass, radius, and in particular, angular momentum. And so our goal is to set an upper limit as a function of the mass. So we're going to look for an equation of state that will be particularly conducive to having high angular momentum, and use that to bound the other ones so that we can find a general upper bound of what's physically possible. To get an idea of what we're looking for, we use a classical approximation. The neutron star is some sort of light spheroid. At uniform density, we have the moment of inertia of such an object is 2/5 mass radius squared. And angular momentum, the maximum angular momentum is from the moment of inertia times the maximum angular velocity. The angular velocity, the star, if it spins too fast, it'll start to tear apart because the particles will go into orbit. So we can set centripetal acceleration equal to gravity. We're using classical approximation, as I said, and get an expression for the maximum angular velocity that the star can have. And combine those two, and we get the maximum angular momentum is proportional to radius times mass cubed, all square rooted. So we're looking for some equation of state that will have as much mass and, more importantly, radius as possible. So we're looking to be able to stack on as much matter as we can stack on. Now, so what we want then is a very stiff equation of state. That means basically the slope of pressure density, in this case energy density, should be as high as possible. Now, if this slope is too steep, dp d rho is speed of sound, and speed of sound cannot exceed the speed of light. So we have an upper bound of how stiff an equation of state could possibly be, and that will give us the most general upper limit we can find. So when we're looking now to support this claim that we want a stiff equation of state, we can compare numerically the different equations of state. There are a lot of speculative candidate theories that are already out there. We can compare stiffer ones versus less stiff ones, and we've been seeing that the stiffer ones do give generally higher angular momentum and higher masses. So here's a plot of the various equations of state. They've all sort of fallen on this curve, and we're still trying to explain why that is. But you can see in the top area, up here, these ones, the yellow and the black, are the stiffer ones, and they're able to get to the higher masses. Now, I should probably mention that the mass is limited by the fact that if it's too massive, the neutron star will collapse into a black hole. So there is an upper limit on that, but the stiffer ones are able to get to the higher masses, and it's likely that this range of equations of state is actually not feasible. It's been ruled out experimentally. So we're looking at this yellow one right now, and it is generally, this is the stiffest we got. And we're looking to set a more precise bound right now. So that's what we have right now. And hopefully we'll find more precise angular momentum and rule out some other equations of state. I'd like to acknowledge Professor Zhou, Kenyon College Summer Science Scholarship Program, Jocelyn Lee, and John Freeman. Thank you.
Questions?
Yeah.
So in a sense, you're just sort of, in terms of the equation of state, just kind of making something up to try to make it support as much angular momentum as possible, and then saying that's setting an upper limit.
Yeah.
It's not really physical in a sense where
It's physically the upper limit on physically possible equations of state. Yeah, correct.
So it's just the causality. We just demand causality. Of course, the stiffest equation of state is the uniform density one. But that's unphysical because the speed of sound is infinite there. So we just demand causality there. So in some sense, if we discover a neutron star that breaks this bound, then there's fundamentally something wrong with our neutron star model. So it's a very generic bound. Of course, there are people who study the realistic equation of state, and actually what Ben plotted there, the yellow line is the stiffest realistic equation of state that is known. We are still working on how to implement our ansatz into the numerical code, and that's a sort of kind of very, there's something wrong that we don't really quite understand how it does. But
did you say some of the lower states you had ruled out through experimental data?
No, they've been recently, people have observed stars of masses that are, neutron stars of masses greater than those. So because they can't produce the high masses, it's likely that they're not actually the correct equations of state. But those are some older models that
So it's slightly misreading that what he meant is that the softer equation of state that typically give the lower mass is ruled out because there's other quantities that we actually put the bound on and searching for the bounds. And if the equation of state is too soft, you cannot really create massive neutron star because it collapses. And by just looking at measuring the mass of a neutron star, you can actually put the bound and get rid of all these soft equation of states. And currently, I think that the observation prefers stiffer side of equation of state. That's what he meant.
Any other questions? Okay. Thank you, Steve.